Okay, this is sections of information from chapters 4 and 5 in the textbook, and we're going to talk about how we symbolize features, basic concepts of map design. So there's different ways of differentiating objects on a map. Basically, we can have changes in category, we can vary the shape, the line type, the pattern, the color, the font. We can have changes in quantity by varying sizes, thicknesses, and colors. And so here are just some examples of things you can do that can help you differentiate one thing from the other. Shapes, sizes, thicknesses, types, colors, patterns, and fonts. Whether we're talking about the size of the font, the color of the font, or the style of the font, they all can impart meaning to elements in a map. So let's talk a little bit about using color. It may be used for category or for quantity. There's a lot of different ones. The HSV color model is one we're going to look at just a little bit. And this is where we have various U's for changes in categories. And so, for example, if you have 5 different categories, you might pick 5 different U's. You can vary saturation or value for changes in quantity. For example, you have something that's in a single red spectrum, but it goes across from light to dark. I made it all the way to 2 slides before I started yawning. It happens every time. Sorry. And you can have a divergence where you go from one extreme to another, going from one color to another to impart sort of a shift from A to B or a negative to positive kind of a scenario. All these are just ways of looking at U, saturation, and value as colors, and how we can use colors to impart information. So how do we make symbols effective? Well, there's an old saying about not reinventing the wheel. Well, that's the big thing with making symbols effective. Stick with conventions or the connotation that goes along with a specific color. But you also have to be aware of things like color blindness. So what are we talking about? Well, as far as convention, things like red crosses for hospitals. Let's see, what else would we have? Stars for capitals, things like that. Those are sort of standard, just conventional things that are the norm, if you will. Then there's connotation. In other words, what does that color sort of imply? If we look at the top map in the center of the U.S., you see that it goes from blue to red. And essentially, this is a map looking at temperatures. And basically what we know is that as we're further north or higher in elevation, during certain times of the year, of course, we would expect significantly cooler weather than what we would as we moved south. And so the convention would be cold is blue, hot is red. And we follow that, or the connotation is that blue is cold and hot is red. Similar scenario is the bottom right. We've got a map of the Gulf of Mexico and the ocean, and we've made all the land elements shades of blue, which we would typically associate with water, and all the water elements shades of brown, which we would typically associate with land. This doesn't follow the connotation of the colors. The colors are not what one would expect for the thing that it is mapping. Now, with color blindness, it becomes an issue, and it's something where you have to think about what these changes in shades might look like to someone else. And so a lot of times the simple solution for that is to make black and white maps, and then simply focus on making effective black and white maps, because they'll work for people who are who have access to the full visual spectrum, as well as people who suffer from color blindness. So let's look at color and quantity. Rainbow maps rarely work on polygons. And the reason is, well, it looks kind of goofy, much like you see the map on the left. It just sort of looks like, you let a 4-year-old loose with a box of crayons and they just started coloring in squares and polygons based on however they felt. And so it doesn't always look really, really good. Whereas with continuous data like rasters, a color ramp, a rainbow ramp, tends to do a very good job. Black and white maps are desirable a lot of times for simple reasons like it's cheaper to print. A lot of scientific journals still charge more if you want to have color images. They are a better choice if you're going to fax a map or copy it on a copy machine. And like I said earlier, they work better for people who are colorblind. When you design black and white maps, it's not the same thing as taking a color map and just printing it off in black and white. That just doesn't work. You need to design your maps in black and white. And one of the first things... Ooh, my bookshelf just about fell over. Sorry about that. The first thing you need to consider is the human eye has the capacity to only differentiate about 5 or 6 different shades of gray. And so as we have more shades, it becomes harder and harder to tell when you look at the map which color you're looking at in the legend. So if you look at the bottom of the screen here, we only have 5 shades, and so you can pick out a color on the map and then find the color in the legend, like the light gray, which is the 27,000 to 100,000. The more different classes you would have, the more different shades of gray you would need, the more difficult it is to associate, for example, that next shade up with the 110,000, or the one above that with a 210, or the one above that with a 300, or the highest one with 480. As you get more and more classes, it becomes harder and harder to pick out the thing you're looking for on the map and match it up to the thing in the legend. So what do we do? A lot of times we're forced to, in addition to those levels of color, we add elements of patterns. Patterns can add additional detail and can take, for example, a color ramp of 4, which is pretty easy to see, and by adding a textural element to it, you can make that 8 or 12. And that all makes it an easier map to understand in black and white. So when we print these sort of things, if we're printing in color, a nice geologic map would look something like you see on the left. If you're going to make that same map but in black and white, it would look more like what you see on the right. So let's talk about the different ways to map data. We have a lot of options within the software, and as you work through the tutorials in the chapter, you'll kind of become aware of more and more of these. You can have a single symbol map where everything's just the same. You can have unique value maps where all attribute information for a particular field, whatever the number of options you have, are the things that get mapped out differently. And you can have quantity maps where we have things like graduated colors, graduated symbols, or dot densities to show us these various quantities of things that are occurring in space. Now, when we look at single symbol maps, that's stuff that we typically use for like nominal data. Unique values typically are categorical or ordinal, and quantity maps are interval or ratio data. So let's talk a little bit about the data. Let's talk about nominal data. These are names or unique identifiers and objects, for example, state names, owners of parcels, tax ID numbers, those sorts of things. Something where, for example, in that image that you see there to the right, we have all these states. They're all mapped in the same colors and all that kind of stuff. And so we're not trying to differentiate or do anything differently. They're all just the states. But we did identify them by their unique identifier, their name. But we didn't give them any individuality in terms of how they're represented. Yeah, typically this stuff is what we would portray on a map as a label. Single symbol maps display all features with the same symbol, combined with labels to portray nominal data. Single symbols, here we have stars representing capitals within each state. Categorical data places features into a defined number of distinct categories. Excuse me. Categories names may be text or numeric and portrayed by different symbols for each category. And so examples would be if we had types of volcanoes. It's not just that they're different types, but it's what those types mean, and that could be something as simple as a stratovolcano, a caldera, or a complex, a shield, or volcanic field. Same way with highways. A lot of times we're just going to portray these features as lines, but is it an unclassified line, an arterial, a freeway, an interstate? We can change the width or the thickness, the color, or the type of line, and from that we can infer additional information about the category of highway or the class. Similarly with land cover, we might look at this whether it's in polygons or a continuous surface, so whether we're looking at individual raster cells or what have you. They've all been categorized as, is it shrub steppe, is it tall shrubland, is it transitional forest, etc. And so all the stuff that meet a criteria are lumped together under a single label. Unique value maps, they have a different symbol for each category or value. Volcano types, road types, geologic units are just some examples of how you can do this. Ordinal data, it's typical of it's a type of categorical data. It ranks categories along an arbitrary scale like low, medium, or high, village, town, city. In other words, there's distinctions that make sense. Grades, best places to live, etc. Ordinal data can be a little more complicated to wrap your head around. Obviously, I want you to read through the textbook, look at the examples and the tutorials, and try to get a better understanding of this, but this is not something I'm going to necessarily test you on. Well, I shouldn't say that, I guess. I typically don't test this unless it's an open sort of resources, open notes, open book, take home type test. But in your online study environment, depending on the instructor, as they make up your exams, they could ask you test questions about this, so maybe you need to learn it a little better. But it's not really sort of the focus of what we're doing, but it does help understand how you map things and what you map and the ways you map them. So interval or ratio, these are data placed along a regular numeric scale, data that supports addition and subtraction. Ratio data places values along a regular scale that has a meaningful 0 point. It supports addition and subtraction, multiplication and division, etc. The meaningful 0 point is important. For example, population. You can't have a negative population. Once there's a 0 point of no people, there's no people. You can't get less than no people. You can't get less than no rainfall. Median rent is sort of that middle value of how much rent is paid in that area. Whatever that value is, it's sort of an absolute there. And so, you can't really have a negative, is what I'm getting at, real numbers. So how do we map numeric data? Well, interval and ratio typically has to be divided into classes before we can map it. We can map it using variations in symbols and size and thicknesses and colors, but in general, the first step with most interval and ratio data is to classify it. In other words, we go from having just an inordinately large number of values into groups or classes of similar values. And once we have classed maps, we can do it a bunch of different ways. The one on the left is a choropleth map, and what you can see here is that we have lumped population per square miles relative to the 1990 census. And if the population of your state is between 1 and 92 people per square mile, it's one color, and then if it's 93 to 232 and so on, and you can see as the population becomes more dense, the color scheme darkens. Now, when we look at the graduated symbol map, notice that we still have all the stars for the state capitals, and some are really big and some are really small. That would be the population of, I'm assuming those to be the populations of the state capitals. But it could be state populations, but I'm pretty sure it's not. Particularly when you look at Florida. Florida has something like 13 electoral votes, which is a lot, indicating that it has a significant population, but it has a relatively small star, because Tallahassee is not a huge city per se. It's bigger than, for example, Charleston, West Virginia, or was it Lexington, Kentucky, or Harrisburg, Pennsylvania. I think it's capital Pennsylvania, I'm not sure. Anyway, point being, by changing the size of the star, you get an idea of which state capitals have more population. We can also use colors for choropleth maps. Here we have a single color ramp. That's what we call when we have a selection of colors that are all sort of, for this example, they're all shades of red. And we change that saturation. So in other words, if you imagine taking a gray color and you just add a little bit of red, and then a little bit more red, and a little bit more red, all the way up until it's just really, really bright red, that is how saturated that becomes in color, as opposed to just having a dull, sort of faint light gray color. And so as we change that saturation, we know that the value of whatever it is we're mapping goes up, just like the color. Now, one problem, if you use too many colors, it can get kind of weird, because it'll do things like it tends to mask certain values. When you have those multiple ramps, it can at times make things misleading, because you start to imply things like cold versus hot, when that's not the point. The point is high to low, and high in this example is cold and low is hot, if you think of it that way. But in fact, if we're looking at population, there's no hot and cold. It's just a poor choice to use that particular color ramp, as opposed to using the multi-color ramp versus a single color ramp. Normalizing classed maps. If the size of the map impacts the measured value, then the data should be normalized. And what does that mean? If the size of the sample impacts the measured value, in other words, by percent for total. If the percent of farms in each state versus the percent of mobile homes in each state, these are things that are somewhat dependent by the size of the states. So you need to show them as a percent, because it's not how many farms have problem X, it's how many farms out of the total number of farms in that state. It's not how many of the homes in the state are mobile homes. It's not how many mobile homes, it's what percentage of the homes are mobile homes. Does that make sense? Anyway, another example is if you use another field. For example, if you divide farms divided by area, mobile homes divided by housing units, they're all ways of looking at this data and normalizing it. For example, if you look at the total number of farms, Texas always looks like it has more farms than, say, for example, Ohio. But if you look at the farm acres versus the total acres, so you calculate like percent farmland in the states, then it becomes a very different animal. And then it also falls into what you define as farmland. Does that count pasture land, or are we only talking about row crop agriculture? How we determine what classifications we use and how we make those classifications have real impacts on our maps. And we can also use unclassed maps, where we just use proportional symbols, or even dot densities, where you can see one dot equals so many people, and then they're scattered appropriately and somewhat randomly across the states in which the population numbers come from, and you get some idea of where people live in the U.S. And you can also do chart maps. I hate chart maps, but don't let my disdain for this particular type of map cause you to not ever choose to use them. There is a place and a time for these maps. I find them to be busy and awkward and difficult to use. Other people like them. That's up to you. Now let's talk about our good old friend MAUP, Modified Areal Unit Problem. So what does this mean? This happens when an arbitrary aggregation units like states or counties influence values. For example, the number of farms is affected by the size of the state. The number of vacant houses is also affected by the population. And so some other thing that we're aggregating data by, some arbitrary boundary, could influence how we look at a particular field. For example, let's look at Texas. Regardless of what we're looking at in Texas, Texas is a very big place. There's a whole hell of a lot of Texas. So what do? Well, if we divided that down and looked at whatever we're looking at by counties in Texas, all of Texas may not deserve to be colored in that dark brown. But then we drop down to the counties, maybe only parts of the counties are. You see what I'm saying? The area unit, the areal unit, the boundary we create has an influence on how we interpret the output. And that's what MAUP is. It's this arbitrary effect of aggregation units. How do we minimize it? Number one thing we do is normalize. Normalize our data by something related to what's causing the problem. And so if we're looking at some value and the states are different sizes, that makes it look misleading. For example, number of farms. Well, then instead of looking at farms, we should look at the density of farms per square mile. So now the farm count is divided by the size of the polygon, and it gives us a better representation of how farmy, if you will, that polygon is. And when you look at these two maps, sheer number of farms, Texas has the most, but when you look at farm density, it's the green belt area there. Oh, maybe not the green belt, but well, yeah, it's mostly the green belt. So we can also normalize vacancies by numbers of housing units. Same concept we had in the last set of slides, but just different example. You can normalize by field percentage, divide each value by the total of the column. So percentage of Congress controlled by each state. You know how many members of Congress there are, you know how many electoral votes or how many representatives there are from each state. Divide one by the other and you can see that, for example, Congress, or California rather, controls 10 to 13% of Congress, where many other states control less than 1% of that. Now, aside from the impact it has on analysis and how misleading it can be, there's also this concept of visual MAUP. And this happens when large polygons tend to dominate the map. They look more prominent and they attract more attention, even if they don't deserve it. So how do we reduce it? We look at other ways of representing that information on maps. So if we're looking at number of farms, maybe we should look at dot density maps. And you can see that when you do that, Texas still has a lot of farms, but you can see the areas where the greater density of farms is. Same way if you do one of these chart maps or a dot density map or some effect similar to that. Just other ways of doing the same kind of things. So let's talk a little bit about rasters. Raster types, we've got two main ones, discrete and continuous. Discrete are when rasters pretend to be polygons or lines. Typically adjacent cells have the same values. You have abrupt changes at boundaries, and it gives you a very inexact definition of a location or shape. Continuous data, you have thousands or millions of potential values, not a lot of adjacent cells that have the same values. In other words, Each one is fairly unique, and the values can change very rapidly sometimes from cell to cell. But that's what continuous data looks like. We can also think of this as thematic rasters and image rasters. Thematic rasters contain quantities that represent map data such as land use or rainfall. They can be continuous or discrete, so you can have rasters that act as areas, like polygons, that do things like tell us about land use. Or we can have continuous surface rasters, like elevation rasters, like a digital elevation model, that show us what the elevation is in a continuous surface. We can also have image rasters, like satellite photos and any number of other types of sensors like that, where they record digital data, if you will. And when they do this, it is all recorded in a raster format. Every cell in the raster, every space in the grid contains one value, and in the case of images, that value is the color to be displayed. Now I want to talk about raster pyramids. At times when you're doing GIS analysis, you'll load up a data set and it'll say, would you like us to build pyramids? And my old standard answer was, you're a few thousand years too late and we're not in Egypt, so why should I build pyramids? Turns out that is nothing to do with these type of pyramids. What you'll find is with large raster data sets, as you try to move around or zoom in or zoom out, the capacity or the need to re-render the image on your computer screen is significant, and it can make it very difficult to move around in ArcGIS and very difficult to make significant changes in what you're doing, simply because the moment you begin to move, there are literally millions of raster cells that then have to be the values have to come up differently on the screen. So what do? Well, we create pyramids. Raster pyramids speed up the display, and the way they do that is they create successive lower resolution copies. Okay, now you remember how as your resolution increases, your data volume goes up exponentially. So to go from 1 to 50 to 1 to 25, or 1 to 25 to 1 to 1250, that means that the volume of data goes up through the roof. Here's the thing though, if you go the other direction and you're already at the 1 to 12.5 and you want to make a 1 to 25 and a 1 to 50 copy like that, that's not as much more data as what you might think. In fact, it's only about 50% of the original data set's size. And once you create it, you can use it a lot of times, and what happens is when you are zoomed out at an appropriate distance, you will be looking at the 1 to 50,000 as opposed to the 1 to 12,500 scale. And when you move around that image, it's much easier and much faster, and it requires, or it causes much less problems for the display. Then once you get to an area that you want and you zoom in, if you will, you look at the lower resolution, or the higher resolution, the more zoomed in look, and things will then display more easily. How do we display thematic rasters? Unique values or discrete colors. We can classify them. We can also stretch them. Stretching is when you take a set of colors like this really strangely colored band that you see in the bottom right, and we simply go from the values that we have in our raster and we stretch them out across the range of colors in that set, and you get something that looks like the bottom. We can also classify it, where we take each of those colors and we create classes that have various numbers in there, and so you get more polygon look, less raster look. Now there's some things that we do when we process rasters that's important to understand. And first, let's talk about slicing. So you might have a raster data set that might have 1 million different values in it. How do you display that? Well, first thing we do is something we can look at called slicing, where we look at the lowest value to the highest value, and then we bin the data. Okay, and what that means is we take that range from lowest to highest, and we divide it by the number of colors we have, 256, and everything that falls in that range of 1/256 of the total data goes in the first bin, the second bin, etc. And ultimately what we're trying to do is represent similar values with similar colors. Now it doesn't mean that we change those numbers. If you pick those cells, you might have two cells that are the exact same shade of green and have different values, but they're going to be within a similar range. With stretching, we recognize that we have a limited number of colors, and at the very, very high and the very, very low, there's not a lot going on. And by not a lot going on, I mean if you look at the volume of data, which would be how high the purple goes in the image on the left, the most of your data is sort of in the middle. And so if we come in one standard deviation, for example, on both ends, and just take all that stuff on each of those ends and put that into one bin each, then that would leave us, what, 254 colors to divide out between the rest of the data. And effectively what it does is it takes that middle part of the data where the most interesting stuff is, where the variability is going on, and that shows more detail. So we have two images here, the original slice, which was just from low to high, versus when we come in one standard deviation on each end, and you can see it doesn't look a lot different, except when you get into some of those places, like in that white area in the bottom left hand corner, you pick up more detail, more variability, because you have less data to fit in the bins, and so effectively the range within the bins gets smaller, and so you see more detail. Image display, I've said before, and I often say that, with rasters, the thing to remember is there's only one number, one value in each cell, and that's true. But there are certain types of rasters that are called that have multiple bands, and so it's a single raster, but it actually behaves more like multiple rasters, like 3, 4, or even maybe 100 different rasters, depending on where the information comes from and what it is. And so if you have a single band image, you would have something like you see there on the left. The one on the right is a 3-band composite, and what this does is it uses a color system where reds, greens, and blues are measured, and then that combination of a value for red, a value for blue, and a value for green are combined to give you a composite true color image. Alright, so let's go back and talk a little bit about stretching images again. Here we have an image raster with no stretch, and then one where standard deviation stretch has been applied. And basically you kind of get the idea. If you look at that picture on the left, you come in one standard deviation, it's kind of where that up and down line is on that normal distribution, and everything to the left of that mark goes into the 0 bin. And on the other side of the hump, you see the same mark going up. Everything that comes in beyond that goes in the 255. So from 1 to 254, all the rest of the data comes in. And in this case, the difference is, look on the images on the right, no stretch versus a standard deviation stretch. See how much more detail you pick up? Stretching maximizes the brightness and contrast within how we visualize the data. And there's different stretches, not just the standard deviation. There's min, max, and others. So you can see how the different stretching types affect the images. Now I mentioned before about the multiple colors, the red, green, blue composites, where you have a red image band, a green image band, and a blue image band. You put them together and you get the composite. This is what I was talking about. So for every color you get a number, and that number would be somewhere between, for example, 0 and 255, and that is how bright or dull, how faint or sharp those individual colors are. And then when you combine those individual colors, you get the real color, the composite color. Some satellite information, particularly things like Landsat, has multiple bands, and so for example, there are 7 different bands in this particular Landsat data we're looking at here, and you can arrange different combinations of bands, so it's not always just red, green, and blue. And so a 321 is red, green, and blue, and that gives you true color. 431 gives you false color. What's false color? Band 4 is the near infrared, and so in place of red we use near infrared, in place of green we use red, and then we use the blue that we've always used, and basically it allows us to see somewhat up into the thermally reactive kind of stuff in the infrared, basically heat and how it responds to it. It also gives us some windows into looking at things like water content as well, and certain mineralogy. The other one over here, 741, it's just a different combination of bands that mean different things. In this example, it's a higher band plus the near infrared plus blue. Indexed color rasters are more or less useless. And so what they are is think of it as a scanned image of a traditionally made vector-based map. But where in the traditional vector-based map you had information about the roads and the points and the polygons, in the scanned raster image the only thing you have is the colors that were on the map. And so, for example, that font or that red text that you see in the top map, if you scanned it, it's going to have if you try to classify it out, it's going to get a value of 3. What does that mean? Absolutely nothing. It means it's red. Okay? That's all these things do. It converts a lot of information into a color. So there's a couple of things in rasters that really come in handy sometimes when you do modeling. One is the zero value, because zero values allow you to do calculations between raster data layers and eliminate spaces where you have a criteria that is utterly lacking. We also have some stuff called Nodata. If you remember how you sort of fit a raster onto the globe, you identify the location of that one corner and then you sort of line it up by moving it around, and so it doesn't always line up perfectly square. And now the raster itself is square, but the values in it don't always fill up all the space, and so you'll get some space that should be part of the raster but it's not. And so what do you do with it? You can make it all zeros, or you can make it no data. If it's no data, you can't do any analysis on it, and this allows you to constrict the field of your analysis. So sometimes no data is really useful, and other times the zero value is more useful. But that is a lesson for another day. Transparency. When we want to showcase information and make people better understand things, for example, a layer of geology, while it does have some meaning, that meaning has a much more tangible feel. It's much more user-friendly and easy to understand when you put it over a hillshade. And hillshade is just shaded relief. It gives something a 3D feel, if you will, by positioning the sun in a certain location given to a elevation model, and then it casts the shadows accordingly. And then by laying the geology transparency, the geology layer of the hillshade, and setting the transparency such that you can see those hillshade shadows below, it helps you understand the patterns you see in the geology.